So the next printing method is inkjetting. It's often compared to 2D inkjetting process. Actually, the first inkjetting printers, the 3D ones, used the print heads from commercial printers like Hewlett-Packard. The same thing for 3D bioprinting. They also started by using the print heads from commercial printers. So these printers are use photopolymers, metals, or wax that cure or harden exposed to UV light or elevated temperatures, or just at room temperature, depending on the material you choose. So the nature of the material jetting allowed for multi-material printing, which is often used to print supports from different soluble material during the build phase. So here you can see the brief summary also. The material jetting used the photopolymer with UV curing process. The NPG process used nanoparticles with support nanoparticles and use annealing. And drop-on demand used the wax-like liquid and dissolvable support materials with the use of solidification. So here's another picture of the printing schedule. The print head moves from left to right. At the same time, curing the material with UV source at the side. So here's also a brief summary. How does this process take place? Let's take a short look at the video about the process.
PolyJet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. PolyJet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The PolyJet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the PolyJet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the PolyJet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. PolyJet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. PolyJet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
So after we took a look on the process, let's also talk about the benefits and limitations of the material or ink jetting. So the jetting printer can produce smooth parts with surfaces comparable to injection molding and very high dimensional accuracy. As you can see, the common layer thickness is only 16 to 32 microns. The parts created with material jetting also have homogeneous mechanical and thermal properties. The multi-material capabilities enables the creation of accurate visual and haptic prototypes. As you might see on the picture below, there's a very accurate model of the human head with all the vascular systems, the brain parts with skeleton by itself, and the soft materials. The material jetted parts, unfortunately, are mainly suitable only for non-functional prototypes because they have poor mechanical properties. They're also photosensitive, and their mechanical properties degrade over time. And also the very high cost of the technology and the material prevent this jetting technology from the widespreading around the customers. So the materials used is most of all is acrylic photopolymers. If we talk about material jetting, or nanoparticles and wax if we talk about NPG and DOD technologies accordingly. So the dimensional accuracy is very high. It's only 0.1% and with a lower limit of 50 microns. The typical build size are from 380 to 250 to 100 millimeters and up to 1 meter to 80 centimeters per 50 centimeters for the industrial ones. It always requires the support, which is not also the cheap material. So it's add additional cost for the process. The material is dissolvable, so you just take it by dissolving after the printing process is finished. Binder jetting. So the binder jetting is a process when you selectively deposit the binder onto the powder bed, bonding specific areas together to form a solid object. After the printing is finished, the parts are in grid state, which means that they have to be sintered in the special oven. The material commonly used in binder jetting are metal, sand, and ceramics, which comes in granular form. So the ceramic-based binder jetting is ideally suited for applications like aesthetics. The metal binder jetting can be used as functional components because they have pretty nice mechanical properties, poorer than SLM and DMLS, which we'll talk about later, but much more cost-effective. So let's take also a look at the video on binder jetting. Here's another scheme of how does this process work. I also will let you read it by yourself. Generally, it discusses the same things I've just told you.